All right, so this presentation is third in a series of presentations for dealing with geoscience data. And just like Michael Jackson's moonwalking, if we take the stuff that we're really interested in, that has to do with the last couple of presentations in the series. But to really get there and get there with in taking in the whole scope of things, we really need to start with the basics. And the first presentation in the series has to do with the universe and the Big Bang. So by this point, we're dealing now with the statistics and probability. And you can probably see back there a bunch of rhinoceros. Do you see anything else in there, by the way? Because the underlying concept of the value of statistics and probability, but even statistics more, what is the real value of that? Do you see anything other than the zebras? Aha, I was afraid of that. So take a look at this one. Now, do you see that? Anything other than zebras?
There is a bird.
The bird.
There's like a lion's face.
It's like a tiger or something like that.
There is grass.
A bear.
I see the bird, I see the lion, I see the zebras. Is there anything else? Have we missed anything? We got it all, pretty much. There may be some subtle stuff. If you look at the zebra in the upper left corner, right below that zebra, is there something in there? I don't know. It looks a little out of place. Anyway, it certainly illustrates the point here. The power of statistics is teasing out subtle ambiguities and understanding deep relationships. It's a heck of a lot deeper than what's the mean and the variance. So let's investigate here a little bit about these topics. And in fact, let's start off with the point that statistics is not probability. No, they're not identical. They have something to do with different things. Statistics can do statistics without probability at all. You might be interested in jumping right into probability, but hold on, statistics, it is a science and it's involved in collecting, analyzing, and interpreting data. And you can draw meaningful conclusions without ever thinking about probability. Statistics deals with the here and the now. Probability is a mathematical tools where you go back and you look at the here and the now, and you find out the probability of things, of taking today's statistical model to predict the future. So the bottom line is probability allows you to predict things into the future. Probability for just probability is boring, but probability to make geoscience predictions, that's wunderbar. All right, so let's think about that a little bit. Probability means we study randomness and its effects on objects of data. And we've looked at what objects are in the past, but we'll kind of refresh a little bit about that. Statistics starts off with observed data. And we have to take our data and infer properties, certainly, of an underlying process. And to do that, we need to sample the data. We establish confidence intervals, and then we resort to hypothesis testing. And we can't get to hypothesis testing without an understanding of the underlying distributions, the fundamental universal distributions of what we're sampling. Sampling in itself is fine, but the sampling is out of a universal infinite bucket of, if we kept on drawing that particular stuff into that particular bucket, was it a Gaussian distribution, or was it binomial, or was it something else? All right. And that ultimately results then is what is the tail of that distribution, and that's what you decide what's the probability of a P90 or a P10 to be an outlier, yes or no. That's where you can finally get to a statistical use that is really very powerful. The example here is blood pressure. You got 30 people and you've got a new test of a new drug, and you run the test on 30 patients. why 30 and why only one drug? Let's just confine it to that situation right now. So we go ahead and do our measurements of blood pressure measurements. And then we have another test where we have another 30 of people that are without the drug. They have no drug at all. And there's statistical questions. Can you use the same people? And then you test them without the drug first and then test them with the drug? Is that statistically equivalent of having 30 with and 30 without? Those are the type of important questions. And if you're talking about people keeling over because of some new drug that you're coming out with, these are very serious questions. In this particular case, a t-test is not a Gaussian distribution when you're comparing these. A paired sample t-test would be used for this analysis in this particular case. Now, when we're dealing with probability, we're dealing with future outcomes based upon a statistical model of today. And that can include yesterday, but is a statistical model that we can predict into the future. In other words, if we have the probability of a Cat 5 hurricane in Houston, for example, say of every a period of years here, let's see, the failure rate is 1 minus 0.02, and that's meaning that the probability of us hitting is 2%. Probability of a similar hurricane in the next 10 years is 1 minus 0.98 to the 10th is about 0.18. That's how you use probability. Let's quickly review here objects and descriptors and how that ties into the labels and similarity. All right, we got to step all the way back to square one for just a moment. Refresh your memory here a little bit. The universe is filled with objects. In fact, we call the universe a big U, and it was a special font we used for that, which indicates the universe is the end all be all. It's the sum of everything. Every object in the universe is in U, and it's filled with objects. Objects themselves have no names, but they are certainly our marks of reality. So if you have the set of all objects, that set of objects in the universe, it has a couple of interesting features. It has a sample count. How many samples are in there? That's, of course, called the cardinality. And then every object in that set is a member. The descriptors are another way to put together a set, and the descriptors identify objects. So say, for example, you have a set of objects, and let's say all the objects are going to be one object, but we're going to have several descriptors. For example, this may be oranges, and this might be red oranges and green oranges. So the descriptors are modifiers of the objects, and labels and descriptors are the same term. They're also called categories. So whatever floats your boat, whatever is your favorite way of describing, that's fine. Descriptors, labels, and categories, it's fine. It all means the same thing. What does have some meat to it here is some objects themselves have no name. How can that work for us? If objects have no name, you don't have any statistics until you have several no-named objects. In other words, without naming it, you may have oranges as one object, and you may have pears as another object, and with no names whatsoever. And yet we all know, in other words, this is universal, basic kind of stuff. The objects have no names, and we can have a collection, a set of oranges. We can have a collection of apples, that sort of thing. Statistics is the branch of scientific analysis devoted to the study of the similarities of objects and descriptors. Similarity here is the important point. That's similarity. In other words, statistics analyzes the similarities of objects or descriptors. So if you have a set of identical data objects, as an extreme, set of identical data objects, they all fit, and they're all apples, there's no statistical meaning in that one, is there? What about you have a set of unique data objects? Everyone's different, but they are unique data objects. In other words, you have one orange, one apple, one pear. What's the statistical meaning there? None. Okay, doesn't mean anything. Statistics has to have a bunch of something to get the similarity. Or we somehow try to infer what's the similarity between objects. That sometimes can be quite complicated. The third thing is that if you have a set of one object, as I described, there's no statistical meaning there because there's no statistics. They're a unique object. So sets and expressing statistical materials, how do we express them? I hope you're starting to get an inkling that there's a thing called set notation. We have already discussed that a little bit. And set notation is a way of mathematically describing what's in a set. I doubt very much that you got this studied. Last time we pointed out that the seventh graders in the island of Luzon in the Philippines are studying sets in seventh grade. But I bet your seventh grade you didn't study sets. So you probably got through high school. I don't even know if you got into statistics in college where they got involved in sets. We got to be careful. The kids are going to gobble us up if we're not at it. And I can tell you, gobbling it up myself, set notation is a very advantageous way to not only state statistics, but how to use it. For example, here we have two objects. They're identical, aren't they? Yeah. Okay, so we got two objects and they're identical. So it can't get more basic than that. Two objects and they're identical. The other important point before we move on is, what does science do? Statistics is a branch of science, right? And science answers questions. It answers the how, but it does not answer the why. That's important, always important. We as people thinking about living in our societies for the last 200 or 250 years, the scientific revolution is going on that way. It's made us quite object-oriented people, materialistic people, the whole world. But it doesn't answer the question why very well at all. In terms of thinking about the big picture, it's an important one to hang in there. Anytime you're doing an analysis and you're giving your presentation, the very last thing, if you have time and you haven't gotten to be a big blabbermouth like me, just to throw in the very last sentence, explain why you're giving this presentation. Why is it of value? Now, statistical predictions are successful or they're failures, aren't they? Or somewhere in between. Successful statistical prediction depends upon wise choice of objects and their descriptors. In other words, what are you choosing here? Before you ever get to this point about the objects and the descriptors, what's the question? That's Rocky's famous question. So after you have the question, and now we're choosing objects and descriptors, if you don't have that second part down pat, just as strong as what's the question, the statistical prediction is going to be pretty wishy-washy. Now, we have 4 horses of basic statistics. This is the first horse, and that's binning in histograms. And you'll see 4 as we go along here. A histogram is a basic statistical tool measuring similarity between a set of objects. And I'm not going to present this presentation without using a set notation. So I'm sorry, you'll just have to wade through this stuff here because there is a map. But as we go through this, I'm going to point out where it is and why it's valuable. So anyway, we got a set of objects, X, and we have a set of histogram bins with these simple properties. Now, the set of objects that we're dealing with are a set of real numbers. So that the real number set is infinitely large. And our data set that we're going to histogram, those objects are all real numbers. There may be 100 of these things. Each one of these is a test data sample. So n equals 100. This is a symbol for the cardinality. And the range of values of those members in X, this is a sample. And it is between an X min and an X max right here. And all those are part of X. So in other words, X min and X max is a range. We have to have that range. And then we make a decision for our bins. How many bins do we want between X min and X max? So bins is another set, just like X. and we use capital letters to indicate sets. So bins is a set based upon X, and how many bins do you want? And we have then is that it's the square bracket set, meaning that it's an ordered set, and it's the minimum plus m minus 1 delta h. Delta h is the bandwidth for the bin width. Delta h is x max minus x bin divided by m. If you say, I want 10 of these babies, or I want 3. Clearly, when you start breaking things up, if you choose m too small, you have a very broad brush and you end up lumping a lot of stuff together. If you make m too large, m is 100, when in fact the data don't have that range, so you're going to have some empty bins, aren't you? Okay, what we have then is the bins themselves, which is a set, depends upon the input data and how many bins do you want. Histo is right down here. The histogram depends upon x and m, and these are the centers. The center is equal to the center updated plus rattling through all your samples. If you're in the nth bin, for example, and this is the counting function that we've discussed about before, and we're going to rattle through all the samples, all the exabins here, and we're going to add up all of those and add them to that one bin right there. And just the way H is the bin minimums and C's are the bin counts. And so the histogram is the bin counts, of course. And here we have, this is a description of what a histogram is, all laid out in all its naked glory. And you might say to yourself, oh, Lordy, do I have to really try to understand all this? Probably not, but it's just Mark Twain. Mark Twain used to say that his wife, she understood the melody of swearing, but she really didn't understand the stanzas. So no matter what depth you have here, you can understand the song of mathematics, but you may not know it in the minute details. And that's okay. The point here is this is what a histogram is. This is how you do it. If you had to sit down and write this thing in Swahili or Fortran or Python or I don't know, write it whatever you want. Another way of thinking about a histogram is it's a mapping operation. It's a mapping function called histo in low caps here with it's just a label, and it maps X into a thing called histo. X is your original set of samples, which are the real numbers, and it maps it into histo. So it's the counts in each of those bins, and those counts are numbers. They're natural numbers. You've got a count of 5, or you have a count of 28, that sort of thing. So it maps going from one domain to the next. It maps from the a sample set in the real number domain to a histogram in the natural number domain. All right, probability is a set of statistical events. What's that all about? We have a probability as a set results in either several objects with one descriptor. In other words, we've got a bunch of apples that we're analyzing here, or it's several descriptors of the same kind of objects. We have apples and oranges and pears, that sort of thing. So we could have an example set of apples 1, 2, 3, or red apples, yellow apples, and green apples. I think you get the idea. Either case, probability, it's a bounded estimate that ranges between complete uncertainty and complete certainty. Do you smell another mapping thing here? Yeah, you're right. If probability does something that says it's a bounded estimate that ranges from complete uncertainty to complete certainty, it's a mapping operation. The probability of a particular event there is going to be between 0 and 1. And we can also think of that as a mapping operation. The probability of this object bounds between 0 and 1. We're back into probability as a real number, but that real number itself is bounded 0 and 1. So probability itself is based upon the histogram, and it's just taking each of your counts and dividing by n. I think that's pretty simple, isn't it? And the complete set of probabilities requires that they all add up to a 1. If they don't all add up to 1, your PDF isn't much good. All right, guess what? Interestingly enough, probability has no units. They're not apples per furlong or miles per second or anything else. There are no units on probability. That's kind of weird, but it's just a count of objects. So it's the natural numbers, starting with a 1 or 0 if you want to. The count of a particular bin might be 0, but there are no units associated with the probability. Another thing about probability is that probabilities, the source of your probabilities, could be discrete or continuous. In other words, you may have a probability of highway speeds in Texas between Austin and Houston. And what's the average speed? That's an example of a continuous probability distribution. A discrete distribution, of course, would be only fixed possible values of probability. So at discrete values of X, the probability is a subset of the PDF of X. And for a continuous function, it's the same thing. So it's all good. There's basic rules of probability. I'm not going to bother. You could mentally pull this corner of this slide over. It describes the basic rules of dealing with probability. The probability itself is of a particular probability of a data object of the D right here. Might be a single object, and D is a descriptor. D is in the set O, or the probability is for that is out of a set. Amounts to essentially the same thing. Now, this is the probability for an individual in terms of the object or the descriptor right here. And the probability set is putting it all together, and that's capital P. And the similar objects might be dogs, cats, hamsters, as you can see there. For a hamster, we have white, brown, and spotted hamsters. There's various rules for dealing with probabilities because they're kind of weird. There are no units. It's a little hard to understand how you deal with these things. So it takes a little while to get under your wing the concept of how you're going to do algebra or do any work with these things. It has to do with what are the relationship between probabilities here. So probability of A, what's the joint probability of A given B, and the probability of B given A. That is useful for the joint probability is given down here. It's the product of the two. So the union, joint probability of A and B, is the product. And exclusive probability would be the intersection. That's the intersection of A and B, and that boils down to addition. If you just keep these two in mind, joint probability, exclusive probability, you multiply and you add. Hey, ladies and gentlemen, if you've gotten this far into it, you're well ahead of 80% of the people that are having to wrestle with probability. So pat yourself on the back. Next topic is information. What's the value of probability? It's, as you can probably guess, it's intimately connected with probability. And information is a property of probability. Information is a probability attribute. In other words, if you have probability, you have the ability of describing the probability, and that's called information. And it's numerical. Information is an attribute of probability composed of three parts. You have an input set of objects that's got some noise. You've got the output, and somewhere between the two, you have a noisy channel. You can't have information mathematically now. Defining mathematical information, that means you've got an input, a noisy channel, and an output. And even the input is noisy, and then the output is noisy. Information itself is the inverse and logarithm of the probability of y given x, and the inverse of that is called the information. Event with a probability of 100%, it's got no information. An event with the probability of 100%. In other words, it's 100% known. In other words, there is no noise, and x is perfect. Received at the other end is perfect. Probability is 100%. There's no information transfer there. It's the same object. You just done a copy paste. Information of two events measures separately as the sum of their self-information. Now, self-information is something a little bit different here. it's two independent events. Whereas before, these had some probabilities. If they're independent events, they measure the separation as the sum of their self-information. And this is a common situation, so they give it a new name, call that self-information. A little bit different from just information. And just because we're having so much fun with that, there's a Shannon information, which is self-information. So you've got self-information, Shannon information. Yeah, okay, that means the same thing, but expresses the information in terms of probability of a random value. So this is like the Shannon information is the probability, and it's minus log to the base 2, and that information does have units. How can that have units if there weren't any units on the probability? There is, because we have assigned the logarithm, who said base 2, or base 10, which would be maybe more common here. So information, if you use log base 2, those are called Shannons. And if you use base 10, those are called Hartleys. Don't ask me why, it's just something you got to get used to if you're going to dip your toe into this stuff. Mutual information is where we're going. That's what's important for us in our geoscience. The mutual information measures the quality of the transmission from source to receiver. And those are the three parts. The source has a probability distribution. It's a noisy source, a noisy channel, and noisy receiver. The practical results have been found in a number of different fields that are important, not just for machine learning, but also for geoscience as well. And for the practical results are feature selection. In other words, what are the right factors, or sorry, I keep using factors. What are the right features that we would use to conduct our statistics? The learning could be unsupervised or supervised. And we're trying to minimize the redundancy in the input and distill the knowledge, maximizes mutual information between a teacher and a student. All these are worthy tests and valuable things that we get out of a topic called mutual information. What about possible solution of all possibilities? In other words, maybe we've got 5 or 6 different things going on all at the same time. An event may be isolated in time from other events, or maybe they are happening synchronously. Could be either that situation, but we're going to say we have M of those. So we have M that are happening. Now that's different from N, which is the number of samples that we have. Maybe N is 100. M might be 3 or 4 things that we're going to be measuring, which could be at different times or at the same time. If the probability of an event is called P sub I, where D is the probability, it's either this one or it's out of a set, we would like to break down the probabilities to make sure they're meaningful. And we ask what's the probability of several events here? If the number of events is N, and then we have our test set X of vectors at I, as I runs from 1 through M, the number of simultaneous events would be M. And that's the number of bins that you have in your histogram. That's the number of probabilities you have in your PDF. Suppose that you have some instance of time, you've got M measurements, and you would have this as a result. You would have probabilities are discrete, or they could be continuous. Number of quantizations is called P, and how many probabilities are there? There's M by N in this case. If they're quantized to 1, p-value is in the range of 0 to 1, of course. And then finally, the last down there, probability distribution. It could be a Bernoulli distribution, for example. It's either 0 or a 1, which we could call it a false or true or a yes or no, whatever one. Those are all called Bernoulli distributions. There's only 2 probabilities. It's not a Gaussian distribution. Gaussian distribution is continuous from minus infinity to plus infinity. But let's restrict it for a second here, a Bernoulli distribution. In the case of this system, this divides our probabilities into 2 states. The true state is 1, where you just sum up the probability and it's true, and then the rest of it, the probability is not true. That's a simple one. Now a little more complicated here, rather than Bernoulli distribution, are microstates. And microstates, they're a special type of system. For example, you have, in this case over here in this little diagram, 4 microstates. Each one of these is either H or T. A hit. What is T? I don't know. I don't remember. I bet you do. So keep it quiet. We'll keep moving along. We got n measurements of time, but at any instant of time, we have m measurements. And they're discrete probabilities because this is Bernoulli. So the probability distribution are all binary. So altogether, you've got H, T, T and H, and T and T. So there are 4 possible total microstates. And then these are 4 microstates. And these are the 4, one macrostate. And here's another macrostate of all the truths. The truths down here are the hits and the not hits. So the point is that the total number of microstates can't be larger than m and n. Now, I know probably by now your eyes are glazing over and you're wondering, what does microstates have to do with finding a little geologic prediction that we want to make about something? Hold on, hang in there. The number of microstates is important. And if we were dealing with a quantum level, if we were looking at a bunch of atoms, for example, and we're looking at electrons and neutrons, those would have a bunch of microstates. And then putting it all together, the macrostate is if we got 8 million atoms all moving in average, and we might measure temperature, pressure, volume, density. On the microstate level, we might have a position of an electron, what's its momentum, and what is its spin. These are the 3 microstates. So please don't ignore this stuff thinking that, oh my gosh, we'll never have microstates. Yeah, maybe not today, but you might. The nice thing about the microstates is it helps you reduce the dimensionality by 1 through normalization.